Time is not a river but a fabric, bending around stars and black holes. Albert Einstein once remarked that the only reason for time is so that everything does not happen at once. This video will show you the breathtaking visualizations that turn the complex math of relativity into clear, tangible shapes. You will see space-time diagrams, gravitational wells, and light cones that make these abstract ideas come alive. By the end, you will gain a new way of seeing the universe, one that reshapes your understanding of reality itself. How does gravity twist the path of light? What does the edge of a black hole truly look like? What hidden structure of the cosmos have you always sensed but never seen? Albert Einstein called it his happiest thought. He pictured a man falling from a roof and realized, in that moment of free fall, the man would feel no gravity at all. This simple yet profound idea, the equivalence principle, shattered centuries of understanding. It revealed that gravity is not a mysterious force reaching across space, but something far more intimate. It is the geometry of the universe itself. This was the seed that grew into his theory of general relativity, a vision where space and time are woven together into a single fabric, a four-dimensional continuum we call spacetime. Think of it not as a static stage, but as a dynamic, malleable entity. The presence of mass and energy, like a planet or a star, tells this spacetime fabric how to curve. In turn, that curved geometry guides how everything within it moves. A planet orbiting a star is not being pulled by an invisible string. It is simply following the gentlest path through the warped landscape the star creates. For ages, since Isaac Newton, time was considered an absolute river, flowing at the same rate for everyone, everywhere. Einstein's insight was that this river has tributaries and rapids. Time itself is relative, stretching and compressing based on gravity and motion. This is not just a mathematical curiosity, it is the operating system of our cosmos. As physicist Kip Thorne has explained, this framework of curved spacetime is the essential foundation for everything from black holes to the expansion of the universe. Understanding this bedrock principle is like learning the alphabet before you read a novel. It allows us to finally see the sophisticated visualizations not as pretty pictures, but as true maps of reality, revealing the hidden architecture that dictates the cosmic dance. So we begin with a simple graph, a blank canvas for the cosmos. On this graph, the vertical axis is time, flowing ever upward. The horizontal axis represents space, the single dimension of length. This is a space-time diagram, our first map of this four-dimensional fabric. Every event in the universe, from a supernova explosion to you sipping your coffee, is a single point on this diagram, a precise location in both space and time. Now, an object is not a single event, but a series of them. Trace the path of a stationary object, like a rock on a planet. Its position in space does not change, so its path is a straight, vertical line upward through time. This path is called a world line. The slope of this world line tells you everything about its motion. A steeper, more vertical line means the object is moving slowly through space but quickly through time. A shallower, more diagonal line means it is moving rapidly through space. The absolute limit is a 45-degree line, the world line of a beam of light itself. This creates a fundamental structure, the light cone. Draw a 45-degree line upward from any event, and you have drawn its future light cone. This cone contains every point in spacetime that could possibly be reached by something, like a signal or an object, traveling from that event at or below the speed of light. It defines the absolute, unbreakable boundary of causality. Any event inside your future light cone is a place you can potentially go or influence. Any event outside it is forever beyond your reach, no matter how fast you travel. Let us make this real. Imagine a spaceship embarking on a journey to Proxima Centauri, a star over 4 light-years away. On our space-time diagram, we plot two world lines. One is for mission control on Earth, a nearly vertical line. The other is for the spaceship, a much shallower, diagonal line arcing out toward the star's location. Because the ship is moving at a significant fraction of light speed, time for the astronauts passes more slowly. This is time dilation. On the diagram, this stretching of time is visible. The ship's world line, from the perspective of Earth, is longer and more drawn out. The astronauts experience less proper time to reach their destination than the mission controllers waiting at home experience. This single visualization transforms the bizarre idea of time slowing down into a clear, geometric fact. It gives concrete shape to the future and the past, showing us that what we can affect and what can affect us is not a vague idea, but a precise, luminous cone etched into the structure of reality itself. This luminous cone is not a solitary structure, but one half of a perfect pair. From any single event in spacetime, the future light cone reaches upward, while an identical cone extends downward into the past. Together, they form a complete double cone, a fundamental shape that carves the universe into distinct and unchangeable regions. Think of a single raindrop falling onto the still surface of a pond. The moment it strikes is your event. Instantly, ripples expand outward in a growing circle. Those ripples represent the absolute maximum speed at which any influence, any information, can travel. In our universe, that speed is the speed of light. Now, the area inside the expanding circle is your light cone. Any point inside that circle can be reached by the ripples, touched by the event's influence. Outside the circle, the water remains perfectly calm, completely untouched by the raindrop's impact. This is the essence of causality. Every event that can possibly affect you lies within your past light cone. Every event you can ever hope to influence lies within your future light cone. And then there is the vast region outside the cones, a place called simply elsewhere. Events in elsewhere are forever disconnected from you. They cannot affect you, and you cannot affect them, because to do so would require a signal that breaks the cosmic speed limit. This is not a technological limitation, but a fundamental rule woven into the geometry of reality. What would happen if you could send a message faster than light? The consequences are not just about breaking a record, they unravel time itself. If you could signal into the elsewhere region from the perspective of another observer, your message could arrive before it was even sent. You could create a paradox, a situation where an effect precedes its own cause. The universe, through this simple, elegant structure of light cones, prevents such chaos. It enforces a consistent timeline for everyone, ensuring that cause always comes before effect. This visualization makes the cosmic speed limit tangible. It is not an arbitrary rule on a cosmic highway sign, but the very slope of spacetime itself. The 45-degree angle of the light cone is the universe's ultimate safeguard. The reason you cannot change the past, and the future remains a place of possibility, not predestination. Those 45-degree lines of the light cone are not always rigid and straight. They bend and warp, pulled by the gravity of massive objects. This brings us to a visualization that makes the slowing of time tangible, the gravitational well. Picture a massive, stretchy rubber sheet representing spacetime. Now, place a heavy weight in the center, like a bowling ball. The sheet sags, creating a deep, curved depression around the weight. This is your gravitational well. The heavier the object, the deeper and steeper the well becomes. Now, imagine two identical, perfectly synchronized clocks. Place one clock deep at the bottom of this well, close to the heavy mass. Place the other clock high up on the gentle slope, far from the center. According to Einstein's theory, time itself flows at different rates depending on where you are in this gravitational landscape. The clock at the bottom of the well, where gravity is strongest, will tick more slowly compared to the clock on the shallow slope. It is not the clock's malfunctioning. Time itself is literally stretched by gravity. The deeper you sink into the well, the more time slows down. This is not just a beautiful metaphor, it is a measurable physical reality. In the early 1970s, physicists Joseph Haefel and Richard Keating performed a now famous experiment. They took incredibly precise atomic clocks, synchronized them with clocks on the ground, and then flew them around the world on commercial airliners. Even at the modest altitude of a jet plane, farther from Earth's center and thus higher up the gravitational well, time should run ever so slightly faster. When the flying clocks returned and were compared to the stationary ones, they were indeed ahead by the tiny fraction of a second that relativity predicted. The experiment had caught gravity in the act, redrawing the map of time. This effect is not a laboratory curiosity. It is essential for the technology in your pocket. The Global Positioning System, GPS, relies on a network of satellites, each carrying an atomic clock. These satellites are in orbit, higher up in Earth's gravitational well where time runs faster than it does on the surface. If the engineers did not constantly correct for this relativistic time stretch, the GPS signals would accumulate errors, and your navigation would be off by several miles within just a single day. From guiding your road trip to exploring the universe, this visualization of time as a landscape of hills and valleys reveals a cosmos where mass does not just tell space how to curve, but time how to flow. That deep gravitational well shows us the shape of time, but we need a complete picture of the entire fabric. The most famous and visceral way to see this is the classic rubber sheet analogy. Think of a vast, perfectly stretched elastic sheet, a trampoline representing the very fabric of space-time. Now, place a heavy bowling ball at its center. The sheet sags dramatically, forming a deep, curved depression around the mass. This is not a separate force pulling space downward. The curve is space itself. It is the geometric manifestation of gravity. Now, take a marble and roll it gently near the edge of this curved depression. Instead of traveling in a straight line, the marble will curve, spiraling inward in an elliptical path around the central mass. You are not watching a force pull the marble, you are watching it follow the contours of the curved surface. This is the essence of orbital motion. The Earth is not being pulled by the Sun, it is simply cruising along the gentlest possible path, a freefall path, through the warped spacetime the Sun creates. These paths have a specific name in relativity, geodesics. A geodesic is the straightest possible line you can draw on a curved surface. On a flat piece of paper, the straightest line is obvious. But on the curved surface of the Earth, the straightest path between two cities is a great circle route, the path airplanes follow. In the curved spacetime of our solar system, the planets follow the cosmic equivalent of these great circle routes, the geodesics dictated by the Sun's mass. This simple analogy makes an incredible idea graspable. We can see how mass tells spacetime how to curve, and how that curved spacetime tells mass how to move. It beautifully illustrates why light, which has no mass, still bends around a massive star. A photon of light is like a tiny, incredibly fast marble rolling across the rubber sheet. As it passes near the deep well of a star, it has to follow the curved surface, its path deflected from a straight line. This was one of the first predictions of general relativity to be confirmed, when astronomers observed starlight bending during a solar eclipse. Of course, the analogy is not perfect. The rubber sheet relies on Earth's gravity to create the downward sag, a force the actual fabric of spacetime does not experience. The real curvature is intrinsic, happening within the four dimensions themselves, not into some external space. Yet despite this limitation, the power of the rubber sheet is undeniable. It gives us an intuitive, visual handle on a concept that is fundamentally mathematical. It transforms gravity from a mysterious action at a distance into a tangible, geometric landscape. We can look at that spiraling marble and finally understand we are living in a universe that is not flat and static, but dynamically curved. A place where every object is constantly navigating the invisible topography of spacetime itself. The gentle curves of our solar system are just the beginning. When gravity becomes truly extreme, spacetime contorts into shapes far more dramatic than a simple bowl. To visualize the most violent objects in the cosmos, we turn to a powerful tool called an embedding diagram. Picture a vast, flat plane representing empty space. Now, a massive object like a star creates a depression, like a gentle dimple. But a black hole warps this plane into something entirely different. A deep, funnel-shaped whirlpool that descends into an infinite abyss. This is not a hole in the ground, but a hole in space itself, a puncture in the fabric of reality. The steep sides of this cosmic funnel represent the incredible curvature of space, growing ever more severe as you approach the center. At a certain point, the slope becomes perfectly vertical. This is the event horizon, the point of no return. Once anything crosses that invisible boundary, the curvature is so absolute that every possible path leads inward, toward the central singularity. Not even light, traveling at the universe's ultimate speed limit, can climb back out. It is the ultimate prison, its walls made not of matter but of geometry. We can watch this geometry in action. Imagine a star wandering too close to a black hole. On our embedding diagram, its path is no longer a gentle orbit. As the star approaches the funnel's lip, its world line begins to spiral, whipping around the abyss in a desperate, accelerating dance. With each pass, it plunges deeper, stretching and tearing under immense tidal forces in a process physicists call spaghettification. Finally, it crosses the event horizon. From our perspective outside, its light dims and reddens, freezing in time as it vanishes from our observable universe. This visualization makes the invisible tangible. The event horizon is not a physical surface you could touch, but a mathematical boundary in space-time, a one-way door from which there is no exit. It is the closest thing we have to an actual edge of the universe, a place where the known laws of physics break down. Understanding this stark geometric reality is the essential first step toward grappling with the deeper mysteries black holes present, like the faint whisper of Hawking radiation that suggests they are not entirely black, or the profound information paradox that questions what truly happens to all that falls in. That abyss of a black hole presents a profound visual challenge, for its geometry stretches toward infinity. To truly comprehend the entire cosmos, from the fiery Big Bang to the most distant future, we need a map that can contain the infinite. That map is the Penrose Diagram. This brilliant visualization performs a kind of magic, taking the endless expanse of spacetime and folding it neatly onto a finite page. The result is a diamond-shaped universe, a simple, elegant form that holds everything. Every event that ever was or ever will be finds its place inside this diamond. Its edges are not boundaries but represent infinity itself, while the sharp points at the top and bottom symbolize the ultimate beginning and end, the Big Bang and the far future heat-death of the cosmos. This process is called compactification. It is like taking the entire, infinite surface of the Earth and mapping it onto a standard classroom globe. The globe is finite, yet it faithfully represents every location without any edges. A Penrose diagram does the same for reality, preserving all the causal relationships, all the possible paths that light and matter can take. Now, let us use this powerful tool to revisit the black hole. On a Penrose diagram, the infinite funnel of the embedding diagram becomes a finite, distinct region. The event horizon is a clean, 45-degree line, and the central singularity is a jagged, horizontal line at the top, representing the end of time for anything that crosses over. We can now trace the world lines of two different observers. One observer remains far away in flat, empty space. their path a gently curving line moving upward through the diamond, from the Big Bang at the bottom toward the future at the top. Their light cones are symmetrical, opening toward the future. But a second observer, one falling into the black hole, tells a different story. As they cross the event horizon, their future light cone, which defines all their possible paths, tips dramatically inward. Every single direction they can possibly take now points irresistibly toward the singularity. There is no going back, not even in principle. Meanwhile, the observer safely outside continues their journey, completely causally disconnected from the fate of the one who fell in. The Penrose Diagram makes this stark division geometrically obvious. It reveals the global architecture of the universe, showing how entire histories are woven together or torn apart. For physicists, this is not just a pretty picture, it is an essential analytical tool. It allows them to study the fundamental properties of spacetime, to ask questions about what information can escape a black hole and how the universe might have begun. It transforms the overwhelming concept of infinity into a manageable shape, a cosmic atlas that fits in the palm of your hand. Within this deceptively simple diamond, we see the profound symmetry and connectivity of all things. A single image linking our moment right now to the birth of the cosmos and its ultimate destiny. This cosmic atlas, with its elegant diamond shape, hints at a startling possibility. Perhaps the entire history of the universe is not a story being written moment by moment, but a single, completed structure. This is the block universe model, a vision where past, present, and future do not follow one another, but simply are. Think of all of spacetime as a solid loaf of bread. The entire loaf exists at once. Now, slice it. Each thin slice represents a single moment in time, a snapshot of the entire cosmos at a particular instant. Your birth is one slice. Your life is a succession of slices, and the distant future is just another slice further down the loaf. In this view, time is not a river flowing from the past to the future. It is a dimension, much like the three dimensions of space. We are simply conscious beings moving through this four-dimensional block, experiencing one slice at a time in a steady sequence, which we call the present. But the loaf itself is static and complete. This idea resolves some of relativity's most famous puzzles, like the twin paradox. Remember the astronaut traveling at near light speed. From our perspective on Earth, her time slowed down, but from her perspective, it was Earth's time that was moving slowly. So, who is actually younger when they reunite? The block universe provides a clear answer. Both histories, the astronauts and the Earth-bound twins, are permanently etched into the four-dimensional block. Their world lines are fixed paths through spacetime. The astronaut's path is simply longer through space, which makes it shorter through time, resulting in her being younger. There is no contradiction, only different perspectives on a single, unchanging reality. Philosopher Hugh Price has argued that this view helps us see the universe as a four-dimensional whole, free from our parochial attachment to the present moment. The feeling of time passing, of a flowing now, is a powerful illusion of our consciousness, not a feature of the external world. This is a profound shift. It suggests that history is not gone, and the future is not unformed. The fall of the Roman Empire is still there in its slice. The last star burning out in the far future is already there in its slice. You are not a fleeting actor on a stage, but a timeless sculpture woven into the permanent fabric of the cosmos. Your entire life existing at once as a complex, beautiful shape in four dimensions. That timeless sculpture of the universe reveals its curves in the most direct way possible, by bending light itself. This is gravitational lensing, a celestial phenomenon where the gravity of a massive object acts like a giant lens, warping the space around it and distorting the light from objects behind it. Think of a funhouse mirror, but on a cosmic scale. Instead of a distorted reflection of yourself, you see a distorted image of a galaxy billions of light years away. A massive galaxy cluster, for instance, creates such a profound dent in spacetime that it twists the paths of light rays passing near it. The light from a distant galaxy, which would normally travel to us in a straight line, instead follows the curved geodesics of this warped space. The result is not a single, clear image of the background galaxy, but often multiple, stretched and magnified copies. Sometimes, when the alignment is perfect, the light forms a complete circle around the foreground cluster, a stunning structure known as an Einstein ring. The Hubble Space Telescope has captured countless examples of these cosmic mirages, revealing ethereal arcs and brilliant rings of light splashed across the blackness of space. These are not artistic renderings, they are real photographs of gravity's handiwork. Each distorted image is a direct snapshot of spacetime curvature, a confirmation that mass tells space how to curve. For astronomers, this is more than just a beautiful proof of relativity. It is a revolutionary tool. By studying how the light is bent, they can map the distribution of mass in the lensing cluster. Incredibly, most of the mass causing this distortion is completely invisible. It is the mysterious dark matter that holds galaxies together. Gravitational lensing acts as a cosmic scale, allowing scientists to weigh what they cannot see. It even helps in the hunt for exoplanets, as the subtle gravity of a distant star and its planets can briefly magnify the light of a star even farther away, revealing the planetary system's presence. Every time we observe one of these stretched and twisted galaxies, we are watching light trace the invisible contours of the universe. We are not just looking at a picture, we are reading a topographical map of reality, where the highest peaks and deepest valleys are sculpted from gravity alone. These cosmic mirages reveal a fabric that is not just curved, but potentially folded. The geometry of spacetime may hold even wilder possibilities than simple hills and valleys. Topology, the branch of mathematics that studies shapes and their properties under continuous deformation, offers a radical new way to visualize time itself. Think of spacetime not as a smooth, flat sheet, but as a dynamic topological surface. This surface could, in theory, contain folds, bridges, and even tunnels. The most famous of these theoretical structures is the wormhole, often depicted as a shortcut, a cosmic subway tunnel connecting two distant regions of the universe. On a flat map, two cities might be thousands of light-years apart. But if spacetime is folded, a wormhole could connect them directly, turning an epic journey into a simple step through a doorway. The mathematics of general relativity does not forbid such structures. In fact, certain solutions to Einstein's equations describe these bridges, known formally as Einstein-Rosen bridges. They are visualized as a kind of throat, a tunnel linking two separate mouths that could be separated by immense distances. Yet, this is where the fantasy meets a harsh physical reality. For a wormhole to be traversable, to be a stable shortcut and not a collapsing trap, it would require the existence of a truly exotic form of matter. This hypothetical substance would need to possess negative energy density, creating a kind of gravitational repulsion to prop the tunnel's throat open against its own immense gravitational pull. We have no evidence such matter exists or is even possible. The pursuit of these ideas leads to an even more mind-bending consequence, the closed Timelike curve. This is the technical term for a path through spacetime that loops back on itself, allowing an object to return to its own past. If you could enter one mouth of a rapidly moving or carefully manipulated wormhole, you might emerge from the other mouth not just in a different place, but at an earlier time. You would have traveled back in time relative to your own starting point. The visualization for this is a world line, that path of an object through spacetime that forms a complete loop, like a knot tied in the fabric of time. Most physicists regard closed time-like curves as severe paradox generators, violating causality and making the universe logically inconsistent. The laws of physics, as we currently understand them, seem to conspire to prevent these loops from forming. A principal physicist, Stephen Hawking, termed the chronology protection conjecture. It is as if the universe has a built-in mechanism to stop time travel and preserve a consistent history. Yet, by exploring these extreme edges of theory, we are not just dreaming of time machines. We are stress-testing our understanding of relativity and quantum mechanics, probing the deepest questions about the nature of reality. Could our universe be one of many in a vast multiverse, connected by a web of these topological bridges? The visualizations of folded time challenge our most fundamental notions of distance and chronology, reminding us that the cosmos is a place of infinite geometric wonder, where even the flow of time itself might be a local and malleable condition. These folded visions of time lead us to an even grander geometric upheaval at the very dawn of everything. The universe's first instants were marked by a growth spurt of unimaginable speed, a period known as cosmic inflation. To grasp this, we must visualize spacetime not just bending but stretching itself apart. Imagine a balloon, blank and tiny, before it is inflated. Now, someone begins to blow into it. The rubber of the balloon expands at a ferocious, exponential rate. This is the universe during inflation, a fleeting but colossal epoch when spacetime itself stretched faster than the speed of light. Think of the galaxies not as objects within this space, but as dots painted directly onto the balloon's surface. As the balloon inflates, every dot moves away from every other dot. No single dot is the center. The expansion is a property of the fabric itself. This simple visualization solves one of cosmology's oldest puzzles, the horizon problem. Observations show the universe has nearly the same temperature in all directions. But without inflation, there simply has not been enough time since the Big Bang for light, and thus heat, to travel from one distant region to another to even out these temperatures. It would be like walking into a room where 2 cups of coffee, placed on opposite sides, have cooled to the exact same temperature without ever being near each other. Inflation provides the stunning geometric answer. Our entire observable universe was once a tiny, microscopic patch where everything was in close contact and could easily reach a uniform temperature. Then, inflation happened, stretching that tiny, uniform patch into the vast cosmos we see today. The exponential stretching is captured in a crucial diagram, a plot of the universe's scale factor against time. The graph shows a nearly flat line that suddenly curves upward in an almost vertical cliff, representing that explosive, inflationary growth. After that initial burst, the curve settles into the more gradual, coasting expansion we see now. This visualization makes the theory tangible. It shows how the universe could be so uniform on large scales, because it all came from a single, well-mixed seed. Even more profound, it reveals the origin of structure itself. During inflation, the quantum vacuum was not perfectly smooth. It was a seething foam of virtual particles popping in and out of existence. These tiny quantum fluctuations, ripples on a scale far smaller than an atom, were caught in the inflationary stretch. As spacetime expanded exponentially, it stretched these minute ripples into colossal, macroscopic wrinkles in the density of matter. These wrinkles became the gravitational seeds for everything that followed. The first over-densities that would, over billions of years, collapse under their own gravity to form the vast cosmic web of galaxies, clusters, and superclusters. Every galaxy, every star, every planet, and by extension us, originated from a quantum whisper amplified by the geometric thunder of inflation. Seeing the universe this way creates a breathtaking bridge. It connects the frantic, uncertain world of quantum particle physics to the serene, grand geometry of general relativity. The microscopic and the macroscopic are not separate realms. They are woven together by the fundamental fabric of spacetime, a fabric that can stretch the smallest of ripples into the largest structures in existence. Mass not only bends the stage of the universe, but it can also set it spinning. Picture a spoon slowly stirring a jar of thick honey. As the spoon rotates, it does not just move through the honey, it drags the honey itself around in a swirling vortex. Anything suspended in that honey, like a tiny leaf, would be pulled along by the flow. According to Einstein's theory, a rotating mass does the very same thing to the fabric of spacetime. This phenomenon is called frame dragging. A spinning planet, a whirling star, or especially a rotating black hole, does not merely create a stationary gravitational well. It twists the spacetime around it into a cosmic whirlpool. This means that the space and time near a rotating object are not just curved, they are being dragged around in a circle. The very grid lines of reality are set into motion. For decades, this was one of general relativity's most subtle and unconfirmed predictions. How could you possibly measure spacetime itself moving? The answer came from a marvel of engineering called Gravity Probe B. This satellite, launched in 2004, was essentially a pristine flying laboratory. Its heart contained 4 of the most perfect gyroscopes ever created, spheres of quartz so smooth that if they were enlarged to the size of the Earth, their tallest mountains would be just a few feet high. The principle was elegant. In a universe without frame dragging, a gyroscope's spin axis, once pointed at a distant guide star, should remain locked in that direction forever, like a cosmic compass. But if the rotating Earth was truly dragging the spacetime around it, the gyroscope's axis would be ever so slowly pulled along with that invisible current. This tiny drift is known as geodetic precession. After more than a year of painstaking data collection, the results were in. The gyroscopes had drifted. The minuscule shift was exactly what Einstein's equations had predicted a century before. The experiment had directly measured the vortex of spacetime stirred up by our own planet. This visualization transforms a baffling abstract concept into a physical reality we have now touched. Frame dragging is not just a curiosity, it has real cosmic consequences. Around a rapidly spinning neutron star or a black hole, the effect is not subtle, it is violent. The dragged spacetime whips matter in the accretion disk to incredible speeds, heating it to millions of degrees and powering some of the most energetic phenomena in the universe. Even the orbits of satellites around Earth must account for this tiny twist in the fabric of reality. We live not in a static, curved universe, but in a dynamic one that can swirl and churn, where gravity has a spin all its own. This swirling vortex of spacetime leads us to a revelation that redefines the nature of reality itself. The universe we perceive, with its 3 dimensions of space and 1 of time, might be a magnificent illusion. The holographic principle proposes that all the information contained within a volume of space can be perfectly encoded on its 2-dimensional boundary, like a cosmic movie being projected from a flat screen. Think of an ordinary hologram, the kind you might see on a credit card. The seemingly 3-dimensional image that floats in the air is not stored in the air itself. All of its information is encoded on the flat, 2-dimensional surface of the plastic film. In a similar, though far more profound way, our rich, 3-dimensional existence, from the flight of a bird to the spin of a galaxy, could be a projection from a vast, 2-dimensional surface at the edge of the observable universe. This is not science fiction, but a serious theoretical framework born from the fiery intersection of black hole physics and quantum mechanics. The story begins with a profound puzzle, the black hole information paradox. When something falls into a black hole, it seems to be lost forever. Its information trapped behind the event horizon. But quantum mechanics insists that information can never be truly destroyed. So, where does the information go? Physicist Leonard Susskind, grappling with this problem, made a startling realization. He calculated that the maximum amount of information a region of space can hold is not proportional to its volume, as you might expect, but to the area of its surface. For a black hole, this surface area is the event horizon. This is like discovering that the number of books you can fit in a library is not determined by the size of the building, but by the square footage of its outer walls. This strange accounting led to the radical idea that perhaps the information about everything that has ever fallen into a black hole is not lost inside, but is somehow smeared and stored on its two-dimensional event horizon. If this is true for black holes, could it be true for the entire cosmos? Could our universe be a holographic projection from a distant, two-dimensional surface we cannot see? This principle challenges our most basic assumptions about existence. It suggests that space-time and gravity are not fundamental, but emergent phenomena. They arise from a deeper, more fundamental layer of reality that operates in fewer dimensions, much like the three-dimensional image of a hologram emerges from the intricate patterns on a two-dimensional plate. This is a potential bridge between the warped geometry of general relativity and the fuzzy probabilities of quantum mechanics, two theories that have stubbornly refused to unite. The holographic universe is a vision where the solidity of the world is a kind of code, a dense information structure that we experience as space, time, and matter. It transforms the cosmos from a container of things into a dynamic network of information, a single, unified whole written on the surface of the infinite. That holographic screen, where reality is projected from a two-dimensional surface, forces us to ask a radical question. What if spacetime itself is not perfectly smooth, but granular, built from tiny, indivisible pieces? We are accustomed to thinking of space and time as continuous, an infinitely divisible fabric where you can always find a point between two other points. But what if, at the very smallest scales, this smoothness dissolves into a fine-grained structure, like the pixels on a digital screen? This is the core idea behind causal set theory, a profound and minimalist approach to uniting gravity with quantum mechanics. In this vision, the fundamental ingredient of the universe is not space or time, but causality itself. The entire cosmos is modeled as a causal set, a vast, growing network of discrete points. Each point represents a single event in space-time, a fundamental grain of reality. The connections between these points are not about distance, but about cause and effect. If one event can influence another, a link is drawn between them. This creates a sprawling, cosmic web where the only thing that matters is the causal relationship between nodes. You can visualize this as an ever-expanding graph, a tangle of points and lines that records the entire history of what caused what. The beauty of this approach is its stark simplicity. It does away with the troublesome infinities that plague other theories of quantum gravity. In a continuous spacetime, the energy of a point-like particle becomes infinite, a nonsensical result. But if spacetime is granular, there is a smallest possible scale, a natural cutoff that prevents these infinities from ever appearing. Furthermore, the theory is background independent. It does not require a pre-existing stage for the universe to play out upon. The stage itself emerges from the network of causal relations. The familiar concepts of space and time, of distance and duration, are not fundamental. They are secondary properties that arise from the pattern of connections in the causal set. How can we possibly get back the smooth, four-dimensional universe we know from such a discrete graph? Think of a fine mesh screen. From a distance, it looks like a continuous, solid surface. You cannot see the individual holes. In a similar way, the vast, dense network of a causal set, when viewed on a large scale, gives the illusion of a smooth, continuous spacetime. The dimension of time emerges directly from the causal ordering. A sequence of events where each one causes the next forms a chain, and the length of the longest possible chains within the set defines the passage of time. Space is what remains, the set of events that are causally unrelated to each other, existing in a kind of cosmic simultaneity. This has a stunning implication for the nature of time. In causal set theory, time is not an illusion as in the block universe, but it is also not a smooth flow. It is a sequence of discrete steps, a cosmic clock that ticks in fundamental, indivisible units. The future is not already out there. It is literally being built, event by event, as new points are added to the growing set. This visualization offers a completely new way to see reality. It suggests that causality is not just a rule within the universe, but the very substance from which the universe is woven. Every interaction, every particle collision, every decision you make, is another point being added to this immense, evolving graph of cause and effect, building the solid world from a foundation of pure relation. From that foundation of pure causality, we arrive at a mathematical expression so profound it seems to erase time itself. The Wheeler-DeWitt Equation is the cornerstone of quantum cosmology, an attempt to apply quantum rules to the entire universe. Its most shocking feature is what it lacks. The variable for time is entirely absent from this fundamental description of reality. The equation does not describe how the universe evolves. It describes the universe in a single, timeless state. Think of the cosmos not as a moving picture, but as a single, eternal photograph. All of reality is captured in one frozen instant, a static wave function that simply is. This seems to contradict everything we experience. How can we reconcile this timeless fundamental picture with the undeniable feeling of time passing, with the relentless march from past to future? The answer may lie not in time itself, but in correlation. Imagine a vast, frozen river. The entire river exists at once, a complete and unmoving block of ice. Now, focus your attention on a single leaf trapped within the ice. As you shift your gaze from one leaf to another further downstream, you get the illusion of movement, of a journey along the river. The leaves are not moving, but your perspective creates a sequence. In the Wheeler-DeWitt universe, time emerges in a similar way. There is no external clock ticking for the cosmos. Instead, different parts of the universe act as clocks for each other. The expansion of space, the vibration of an atom, the burning of a star, these are all physical processes that change relative to one another. We call that sequence of relative change time. Your watch does not measure some universal flow. It simply correlates its internal mechanism with other processes in the universe, like the rotation of the Earth. Physicist Julian Barbour has championed this view, arguing that time is nothing but a complex web of these relationships. He suggests that what we perceive as the past is just a different configuration of the universe, a different arrangement of all its parts, which our brains sequence into a story. The future is another configuration, but all configurations exist permanently within the timeless solution of the Wheeler-DeWitt equation. This has a staggering philosophical impact. It suggests that change is the ultimate illusion. The Big Bang is not a moment in the past. It is simply a region of the universal wave function. Your birth, your life, and your death are all equally real and present in this eternal now. This timeless perspective might be the key to uniting general relativity with quantum mechanics. Both theories have struggled with the concept of time. In relativity, time is flexible and relative, but it is still a dynamic part of the geometry. In standard quantum mechanics, time is an external, absolute parameter that is not treated quantumly. The Wheeler-DeWitt equation makes a bold sacrifice. It removes time entirely from the quantum description of gravity, potentially creating a consistent framework for both. It invites us to consider a reality where nothing ever happens. The universe does not evolve, it just is, a fixed and magnificent sculpture of infinite correlations. We are not travelers moving through this sculpture. We are part of its permanent shape, and our journey through life is the lens through which we experience one thread of its intricate, timeless design. A black hole's event horizon is no longer confined to deep space. We can now create its analog in a laboratory tank of flowing water. This is the frontier of analog gravity, where carefully controlled fluid dynamics or exotic states of matter like Bose-Einstein condensates mimic the extreme geometry of curved spacetime. The core principle is a beautiful universality. The same mathematical equations that describe light trapped by a black hole also govern the behavior of other waves in a moving medium. Picture a vortex, a whirlpool draining water. The water flows faster and faster as it approaches the drain's center. At a certain critical point, the inward flow velocity of the water exceeds the speed at which ripples or surface waves can travel outward. Any wave crest that forms beyond this point is dragged inexorably inward, unable to escape the pull of the drain. This is a direct analog of a black hole's event horizon, but for sound waves instead of light. The point of no return for the water ripples is the sonic horizon. Researchers have used precisely this setup to detect an analog of Hawking radiation, one of the most elusive predictions in theoretical physics. In the quantum vacuum, pairs of virtual particles constantly flicker into existence and annihilate each other. At a real black hole's event horizon, the immense gravity can tear such a pair apart, with one particle falling in and the other escaping as a faint glow of radiation. In the water vortex analog, the sonic horizon does something similar to the quantum fluctuations in the fluid. It is thought to spontaneously generate pairs of ripples, one trapped inside the horizon and one radiating outward as a measurable wave. While not identical to the astrophysical phenomenon, observing this effect in a tabletop experiment provides stunning support for the underlying quantum mechanism. These analog systems are more than just clever demonstrations. They are testbeds for the wildest ideas in quantum gravity, allowing physicists to probe conditions that are otherwise impossible to recreate. By tuning the flow of a superfluid or the density of a condensate, they can simulate not just black holes, but expanding universes and other cosmic geometries. This brings the most abstract concepts in theoretical physics into a realm where they can be touched, measured, and directly observed, revealing that the deepest principles of the cosmos can echo in the flow of water and the whisper of sound. Those sonic ripples in a water tank are a whisper compared to the cosmic thunder they mimic. When massive objects like black holes spiral together, they do not just create a whirlpool in space, they set the entire fabric of spacetime ringing. The result is a gravitational wave, a ripple in the geometry of reality itself. Picture the most placid pond you can imagine, its surface a perfect, flat sheet. Now drop two heavy stones into the center. As they splash and circle each other, they send out expanding, concentric rings of ripples across the water's surface. A gravitational wave is the four-dimensional equivalent of those ripples. It is not a wave in spacetime, it is a wave of spacetime. The very grid of the universe is stretching and compressing as the wave passes through. The effect is minuscule but profound. Imagine a perfectly circular ring of floating marbles on our pond. As a ripple passes, the circle would briefly distort, stretching into an oval, then compressing, then stretching in the perpendicular direction. A gravitational wave does the same to space itself. If you were inside a passing gravitational wave, you would see a circle of test particles stretch one way and squeeze the other, over and over. Your own body would be minutely distorted by this geometric tremor, though you would never feel it. Detecting this infinitesimal shudder required one of the most sensitive instruments ever built, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Each LIGO detector is an L-shaped fortress against vibration, with arms 4 kilometers long. Inside each arm, a laser beam is split and sent racing down two perfectly perpendicular vacuum tunnels. The beams reflect off mirrors and race back to recombine. In calm spacetime, the beams return perfectly out of sync, canceling each other out. But when a gravitational wave passes, it literally changes the length of the arms. One arm gets infinitesimally longer while the other gets shorter. Then they switch. This tiny mismatch, smaller than 1/10,000th the width of a proton, causes the laser beams to flicker back into sync for a fraction of a second. That flicker is the signature of a space-time earthquake. On September 14, 2015, both LIGO detectors, separated by thousands of miles, recorded that exact flicker. The signal, named GW150914, was a perfect cosmic chirp. Its waveform precisely matched the prediction for two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging over 1 billion light-years away. For the first time, we had directly observed the dynamic vibration of spacetime, a stunning confirmation of a prediction Einstein made a century ago. This visualization makes the fabric of the universe feel alive. It is not a static stage, but a dynamic membrane that can quiver and ring like a colossal drum. We are no longer just seeing the cosmos, we are listening to it. Every new chirp and rumble is a direct message from the most violent events in existence, a new sense with which to explore the hidden geometry of the dark. The simple funnel of a Schwarzschild black hole is just the beginning. To grasp the true nature of these cosmic engines, we must step into a more dynamic and complex geometry described by the Kerr metric. This is the mathematical blueprint for a rotating black hole, and it reveals a structure far richer than a static pit. At its heart lies not a point-like singularity, but a ring, a whirlpool of infinite density spinning at a significant fraction of light speed. This rotation does not just stir the black hole. It churns the very spacetime around it into a vortex so violent, it creates a new region of no escape, the ergosphere. Picture the black hole not as a single funnel, but as a spinning sphere surrounded by a flattened, oblong shell. This shell is the ergosphere, a region where the frame dragging is so powerful that spacetime itself is whipped into a torrential flow. Inside the ergosphere, it is impossible to stand still. Every object, every particle of light, is compelled to move in the direction of the black hole's spin, caught in a cosmic current from which there is no resistance. The event horizon still lies within, the true point of no return, but the ergosphere is a realm of incredible energy. Here, a theoretical process known as the Penrose process could allow for the extraction of a black hole's rotational energy. Imagine an astronaut venturing into the ergosphere and firing a rocket to split a particle in two. One fragment falls through the event horizon, lost forever. But if the split is timed perfectly, the other fragment could be flung out of the ergosphere with more energy than the original particle carried in. This extra energy is stolen from the black hole's own spin, slowing it down minutely. This is not science fiction, but a direct consequence of the Kerr geometry. A hint that black holes are not just sinks of gravity, but potential power plants. The ring singularity at the center presents another profound departure from the simpler model. Because it is a ring and not a point, the bizarre mathematics of the Kerr metric suggests the possibility of pathways through it, tunnels to other regions of spacetime, though whether these are physically real or mathematical artifacts remains one of the great unanswered questions. Understanding these rotating monsters is essential, for they are thought to be the engines of the most luminous objects in the universe, the active galactic nuclei and quasars whose brilliance outshines entire galaxies. The Kerr metric transforms our visualization of a black hole from a simple pit into a spinning maelstrom of energy and geometric wonder, a testament to the breathtaking complexity hidden within Einstein's equations. That spinning chaos of a black hole gives way to a geometry of breathtaking grandeur when we step back to view the entire cosmos. To map the universe on its largest scales, we use the Friedmann-Lemaitre-Albertson-Walker metric, a mathematical description of a perfectly smooth and expanding spacetime. This framework transforms the history of the cosmos from a sequence of events into a single, evolving shape. Imagine space as a vast, three-dimensional grid, with galaxies fixed to its intersections. As time moves forward, the entire grid itself stretches, causing every galaxy to recede from every other. The universe is not expanding into anything, the grid itself is simply growing, carrying the galaxies along for the ride. This metric reveals that the overall geometry of this cosmic grid can take one of three fundamental forms, each with a dramatic implication for the universe's fate. The first possibility is a flat universe. Here, the rules of Euclidean geometry we learned in school hold true. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. This is an infinite universe that will expand forever, gradually slowing to a halt. The second geometry is spherical, a universe with positive curvature. Think of the two-dimensional surface of a balloon. On a balloon, parallel lines eventually cross, and a triangle's angles add up to more than 180 degrees. A three-dimensional spherical universe would be finite but without any edge, looping back on itself. In this scenario, the expansion could eventually stop and reverse in a big crunch. The third possibility is a hyperbolic universe, one with negative curvature. This is the hardest to visualize, but it resembles the shape of a saddle or a potato chip. Here, parallel lines diverge, and a triangle's angles add up to less than 180 degrees. This would be an infinite, open universe that expands forever at an accelerating rate. Which of these shapes is our true cosmic home? The answer is written in the oldest light we can see, the cosmic microwave background. This faint afterglow of the Big Bang carries tiny temperature variations, hot and cold spots that act as a cosmic ruler. By meticulously measuring the apparent size of these spots, astronomers have determined that the geometry of our universe is extraordinarily close to flat. This observational triumph is a direct result of applying the FLRW metric, connecting a fundamental geometric concept to the light from the primordial fireball. This visualization does more than just describe the present. It charts the entire cosmic story from the initial singularity to the distant future. It tells us that we live in a universe whose expansion is accelerating, likely driven by the mysterious force we call dark energy. Seeing the cosmos through this lens makes its entire evolution a single, geometric narrative, a story where the fate of all things is written in the invisible curvature of space itself. A spacecraft sits at rest, enveloped in a bubble of manipulated spacetime. Ahead of it, the fabric of the cosmos contracts, pulling distant stars closer. Behind it, spacetime expands violently, pushing the point of departure impossibly far away. The ship itself rests within a flat region, a pocket of normal physics, not moving through space but instead being carried by the wave in the fabric itself. This is the Alcubierre warp drive, a theoretical concept that offers a loophole in the cosmic speed limit. While nothing within the bubble can exceed light speed, the bubble itself, the distortion in spacetime, is not so constrained. It could, in principle, cross interstellar distances in a time frame that would make exploration feasible. The visualization is profoundly elegant, a surfboard riding the waves of reality rather than fighting against them. Yet this elegant geometry comes with a formidable price tag. The mathematics of the Alcubierre metric requires a very specific kind of fuel, a form of matter with negative energy density. This so-called exotic matter would possess the bizarre property of creating gravitational repulsion, warping spacetime in the opposite way that normal matter does. It is this negative energy that would contract space at the bow of the bubble and expand it at the stern, creating the necessary wave. While we have observed subtle quantum effects that hint at negative energy, like the Casimir effect, the sheer amount and stability required for a warp drive remain firmly in the realm of speculation. This visualization, for all its theoretical nature, does more than just dream of starships. It forces us to confront the fundamental architecture of physical law. Could a sufficiently advanced civilization learn to engineer spacetime itself, treating the metric not as a fixed background, but as a dynamic material to be shaped? The Alcubierre drive illustrates that the ultimate limits on travel may not be about speed, but about geometry. It pushes the framework of general relativity to its logical extreme, asking whether the rules we have uncovered are absolute barriers or simply challenges waiting for a deeper understanding. Gravity, the geometry of spacetime, holds a secret identity. It may also be a manifestation of thermodynamics, the science of heat and disorder. This connection, one of the most profound in modern physics, is revealed through the humble black hole. For decades, these objects were thought to be simple, defined only by their mass, spin, and charge. They were cosmic vacuums, swallowing everything and emitting nothing, perfect paradoxes that seemingly destroyed information. Then, a young physicist named Jacob Bekenstein made a radical proposal. He suggested that black holes are not featureless, but must possess entropy. Entropy is a measure of disorder, the number of ways a system's microscopic parts can be arranged. In any ordinary object, its entropy is proportional to its volume. A larger box of gas has more ways for its molecules to be jumbled than a smaller one. Bekenstein argued that a black hole's entropy is not proportional to its volume, but to the surface area of its event horizon. The larger the black hole's surface area, the greater its entropy. This was a staggering leap. It implied that all the information about what fell into the black hole, every atom of a star, every page of a book, was not lost inside the abyss. Instead, it was somehow encoded, pixelated, onto the two-dimensional surface of the horizon. To visualize this, picture the event horizon not as a smooth, mathematical boundary, but as a vast, shimmering membrane composed of unimaginably tiny tiles. Each tile is a single unit of information, a bit, with an area equal to the Planck area, the smallest possible unit of area in the universe. The total number of these tiles, the total information capacity of the black hole, is simply its horizon area divided by this fundamental pixel size. This single visualization transforms the black hole from a cosmic plug hole into the universe's ultimate hard drive. Stephen Hawking initially disliked this idea, as it seemed to violate thermodynamic laws. To have entropy, an object must also have a temperature, and a black hole with a temperature should glow. Hawking set out to prove Bekenstein wrong, but his calculations yielded an even more shocking result. He discovered that black holes do, in fact, have a temperature. Due to quantum effects at the very edge of the event horizon, black holes slowly emit a faint glow of radiation, now known as Hawking radiation. They are not perfectly black, and they slowly evaporate over astronomical timescales. This revelation completed the thermodynamic picture. A black hole has entropy, temperature, and radiates energy, just like a hot piece of coal. This single insight bridged the chasm between the two great pillars of modern physics: general relativity, which governs the very large, and quantum mechanics, which governs the very small. It suggests that spacetime itself is not a cold, geometric stage, but a thermal, dynamic substance with its own heat and disorder. The event horizon is not just a point of no return, it is a hot surface. This thermodynamic view of gravity leads directly to the holographic principle, the idea that our three-dimensional reality might be a projection from a two-dimensional surface. It forces us to see the fabric of the cosmos not just as something that bends, but as something that breathes, with a temperature and a hidden inner life, forever changing our conception of what reality is made of. That hot surface of a black hole, with its temperature and entropy, is a direct consequence of a deeper, more universal truth. At the heart of everything we have explored lies a single, elegant set of equations, the master recipe for the cosmos. The Einstein field equations are the fundamental engine of general relativity. the mathematical embodiment of the idea that matter tells spacetime how to curve. While they may look intimidating, their core concept is beautifully simple. Think of them as a cosmic cookbook. On the left side of the equation, you have your ingredients, all the matter and energy present in a region of the universe. On the right side, you have the final product, the precise curvature of spacetime that those ingredients produce. The equal sign is the instruction, the fundamental law that binds them together. Just as flour, water, and yeast combine in specific proportions to determine the shape and texture of a loaf of bread, the distribution of mass and energy in a region dictates the exact geometry, the hills and valleys of the space-time fabric. The strange symbols in the equation, the tensors, are simply a precise language for describing complex, multi-dimensional relationships. The Ricci tensor, for instance, describes how the volume of a small ball of test particles would change as it moves through the curved space, a measure of the stretching and squeezing. The stress-energy tensor is a comprehensive inventory of all the energy, momentum, and pressure at a point. Together, they form a dialogue, a dynamic relationship where the content of the universe and the shape of the universe are in constant conversation. This is not a static picture. The equations are alive, describing how curvature evolves in response to moving matter, and how that moving matter, in turn, follows the curves. When you solve these equations for the empty space around a single star, you get the gentle, funnel-like curvature of the Schwarzschild metric, which dictates the orbits of planets. When you solve them for a rotating mass, you get the twisted vortex of the Kerr metric. The path of a planet is not commanded by a force, it is computed by the geometry. The planet simply checks the local curvature, described by this equation, and follows the straightest possible path through it. Even the bending of starlight during an eclipse is a direct output of this cosmic calculation. The light has no mass, so it does not appear on the ingredient side of the equation, but it still must travel through the curved geometry on the other side, its path deflected by the warped landscape. Grasping this visualization transforms the equation from an opaque string of symbols into the universe's operating system. It is the ultimate expression of unity in physics, showing that the grand dance of galaxies and the fall of an apple are both manifestations of a single, geometric rule written into the foundation of reality. Your own personal clock carves a unique path through the cosmos, a world line with its own inherent length. This is the concept of proper time, the time that is measured by a clock moving along its specific trajectory. It is the most intimate and objective measure of time you possess, an invariant quantity that all observers, regardless of their motion, will agree upon when they examine the history of your journey. Think of your world line not just as a line on a graph, but as a four-dimensional thread weaving through the fabric of spacetime. The length of that thread, measured in units of time, is your proper time. Just as the shortest distance between two cities is a straight line, the longest proper time between two events in spacetime is the path of an object that does not accelerate, the path of maximum aging. This geometric view transforms the twin paradox from a confusing puzzle into a clear visual fact. Recall the astronaut twin who travels to a distant star at near light speed. On a spacetime diagram, her world line is not straight. To leave Earth, travel to the star, and return, she must accelerate, turning her path into two diagonal segments connected by a curve. This path through spacetime is geometrically shorter than the straight, vertical world line of her earthbound brother. Since the proper time is the length of the world line, her path is literally shorter through time. She experiences less duration, less aging, and returns younger. There is no symmetry to break, only two paths with two different lengths, permanently etched into the block universe. This is why time dilation occurs. It is a direct consequence of the geometry of the paths we take. Your proper time is your anchor in the relativistic universe, a personal measure that remains true only for you. revealing that the flow of time is not a universal constant, but a personal odyssey shaped by your journey through the cosmos. That final, fading glow of Hawking radiation forces us to redraw the map of a black hole's entire existence. We need a new kind of diagram, one that can chart its birth, life, and ultimate quantum death. The conformal diagram for black hole evaporation does exactly that, stretching and compressing spacetime to fit the entire epoch onto a single page. It begins familiarly, with the standard Penrose diamond representing the classical black hole. The event horizon is a clean, 45-degree line, and the central singularity is a jagged horizontal boundary at the top. But then, quantum mechanics enters the scene. As Hawking radiation streams outward from just outside the horizon, it carries away energy. This energy loss is equivalent to a loss of mass. On the diagram, this process is visible as a gradual, inward curve of the event horizon itself. The once straight line begins to bow inward, shrinking over time. The black hole is evaporating. The most dramatic moment comes at the end of its life. As the black hole's mass approaches zero, the event horizon curve tightens into a tiny, closed loop and then simply vanishes. The singularity, the classical point of infinite density, may also dissolve, replaced by a smooth, non-singular endpoint. The diagram shows the entire spacetime geometry closing up like a healed wound, leaving behind only empty space and the faint whisper of the emitted radiation. This visualization is not just a pretty picture. It is a battleground for one of physics' greatest puzzles, the information paradox. If the black hole and everything that fell into it simply disappear, then the information about that matter is permanently lost from the universe, violating a sacred principle of quantum mechanics. The conformal diagram makes the stakes clear. One proposed resolution, the firewall scenario, suggests that the evaporating horizon is not a gentle boundary but a searing wall of energy that burns up anything trying to cross, preserving information in the chaotic aftermath. Another idea posits that a tiny, stable remnant is left behind, a cosmic cinder storing all the fallen information forever. The diagram helps us weigh these possibilities, showing how each one changes the geometry of the final moments. Seeing a black hole not as an eternal prison but as a dynamic, evaporating object completely shatters the classical view. It forces quantum mechanics into the heart of gravitational physics, suggesting that spacetime itself might be an emergent property of more fundamental quantum bits. This humble diagram, mapping a black hole's life from violent formation to quiet dissolution, is our best guide to the edge of a unified theory, a place where the geometry of gravity and the randomness of the quantum world must finally learn to coexist. That faint, almost invisible glow of Hawking radiation is a whisper from the abyss. But there is another, far more profound light that fills every corner of the cosmos. It is the cosmic microwave background, the remnant heat from the Big Bang itself. This all-pervading energy is not a featureless fog. It is a detailed snapshot of the universe at only 380,000 years old, a time when it first became transparent. The geometry of this afterglow is the universe's birth certificate, and its subtle patterns tell the story of everything that followed. All sky maps from missions like WMAP and Planck reveal this geometry in stunning detail. They show a nearly uniform glow, but one imprinted with tiny variations, hotter and colder spots that differ by only millionths of a degree. These are not random imperfections. They are a direct image of the primordial density variations, the seeds from which all cosmic structure would grow. The geometry of these patterns is a cosmic fingerprint, and its details are exquisitely sensitive to the shape of the universe itself. Imagine space itself could be flat, spherical, or hyperbolic. The light from the cosmic microwave background has been traveling for over 13 billion years to reach us, and the path it took depended entirely on the large-scale curvature of the cosmos. On a perfectly flat geometry, The hot and cold spots would appear to us at a certain characteristic angular size. If the universe were positively curved like a sphere, the light rays would converge, making the same physical spots appear larger on the sky. If it were negatively curved like a saddle, the light rays would diverge, making the spots appear smaller. When scientists measured these spots with incredible precision, they found their size was consistent with a universe that is geometrically flat. This single observation, this geometric fact written in ancient light, tells us the fate of the cosmos and confirms a critical prediction of the inflationary model. The inflationary burst stretched the infant universe so dramatically that any initial curvature was smoothed into the flat geometry we observe today. But the geometry tells us more. By analyzing the intricate patterns of these temperature fluctuations, cosmologists can read the composition of the universe. The specific statistics of the hot and cold spots reveal how much of the cosmos is ordinary matter. How much is the mysterious dark matter that provides the gravitational scaffolding for galaxies? And how much is the dark energy driving the accelerated expansion? This visualization connects the grandest scales to the earliest moments. Every galaxy, every star, and every planet originated from a tiny density fluctuation, a minuscule wrinkle in spacetime that was stretched by inflation and then frozen into the cosmic microwave background. When you look at a map of this ancient light, you are not just seeing a picture of the young universe, you are reading a topographical map of its potential. You are seeing the blueprint for the cosmic web, a geometric prophecy written in the fire of creation, a direct link between the quantum ripples of the beginning and the vast, structured cosmos we inhabit today. This elegant geometry of spacetime holds a deep and beautiful secret, a hidden order beneath the shifting perspectives of different observers. That order is symmetry, and the key to unlocking it is the concept of an invariant, a fundamental quantity that remains unchanged no matter how you move through the universe. In our daily lives, we are surrounded by invariants. The distance between 2 points in a city remains the same whether you measure it in miles or kilometers. The geometry of a snowflake is identical even if you rotate it. In the world of relativity, where time and space are fluid and personal, we need a new kind of invariant, one that blends them together. This is the spacetime interval. It is the true, objective distance between any two events in the four-dimensional fabric of reality. While two observers moving at high speed relative to each other will fiercely disagree on how much time passed between two events and how far apart they were in space, they will always, without exception, agree on the value of the spacetime interval between them. This is not a compromise, it is a fundamental geometric truth. We can see this harmony play out on a Minkowski diagram, the very map of spacetime we began with. Picture two events like two flashes of lightning. One observer, at rest, draws their coordinate grid with perpendicular space and time axes. They measure a certain amount of time and a certain spatial distance between the flashes. Now, a second observer, moving at a constant velocity, has their own perspective. Their axes on the diagram are tilted inward, a direct visualization of how their measurements of space and time are mixed together. They will record different values for the time separation and the space separation. But when both observers calculate the spacetime interval, a special combination of their time and space measurements squared, they will arrive at the exact same number. On the diagram, this invariant interval is the length of the hypotenuse of a right triangle formed by the events, a length that does not change even as the grid lines tilt and shift. This is the profound elegance at the heart of Einstein's theory. The universe is not a chaotic place where every measurement is subjective. Instead, it provides a stable, geometric foundation. The spacetime interval is the true reality, while our individual perceptions of time and space are merely different shadows cast by this four-dimensional object. This principle of invariance guided physicists to the heart of modern physics. The search for quantities that remain unchanged under transformations, whether in space-time or in the abstract spaces of particle physics, led directly to the powerful framework of gauge theories, which describe the fundamental forces of nature. So when you feel disoriented by the relativity of time and space, remember the invariant interval. It is the universe's way of assuring us that beneath the whirl of different viewpoints, there exists a beautiful, permanent, and deeply geometric truth. This final geometric truth is now stepping out of our diagrams and into our living rooms. Virtual reality and artificial intelligence are poised to revolutionize how we see and experience the cosmos. With a simple headset, you can soon fly directly into the swirling vortex of a black hole's ergosphere, feeling the visceral pull of frame dragging as space itself whisks you along. You could stand on a virtual planet and watch gravitational waves, those ripples in space-time, wash over you, seeing the very grid of reality stretch and compress in real time. Projects like the NAS, a black hole VR experience, are already offering glimpses of this future, transforming us from passive observers into active explorers of relativistic landscapes. These are not just pre-rendered movies, they are dynamic simulations built on the very mathematics of Einstein's field equations. Artificial intelligence accelerates this revolution, generating complex spacetime models that would take human programmers years to calculate. An AI can simulate the chaotic collision of two neutron stars or map the intricate light paths around a rotating Kerr black hole, creating immersive environments from its solutions. This new wave of visualization makes the abstract tangible, turning esoteric concepts into intuitive bodily experiences. You do not just learn about time dilation, you live it, watching your own virtual clock slow down as you accelerate toward a star. This is the next frontier in communicating the universe's deepest secrets, a tool that enhances public understanding and fuels scientific discovery itself. By experiencing relativity firsthand, patterns and connections emerge that might otherwise remain hidden in pages of equations. These technologies promise to democratize cosmic wonder, placing the most extreme environments in the universe within reach of anyone with curiosity. A child can navigate the warped space near a pulsar, and a student can manipulate the variables of a wormhole, testing its stability. This is more than just education, it is inspiration, planting the seeds for the next generation of physicists who will not just study these shapes of time, but will learn to speak their language fluently. We have wandered through a gallery of mental models, each frame revealing a new facet of time's architecture. From the sagging rubber sheet to the finite diamond of the Penrose Diagram, these are not mere illustrations but conceptual bridges. They translate the dense language of tensor calculus into a visual poetry our minds can grasp. That gentle curve in the spacetime fabric around a star suddenly makes the bending of starlight feel inevitable. The tipping light cones near a black hole transform its event horizon from a vague idea into a geometric certainty. The inflationary balloon stretching the quantum foam into galaxies connects the unimaginably small to the cosmically vast. These shapes allow us to hold the universe in our hands, to trace its contours with our fingers. They reveal that spacetime is not a static container we move through, but a dynamic, elastic entity that breathes, twists, and evolves. It is an active participant in the cosmic drama, not a passive stage. This is the ultimate power of a great visualization. It grants us a new sense, a way to see with the mind's eye what was once reserved for the language of mathematics. Carl Sagan once reflected that somewhere, something incredible is waiting to be known. These shapes of time are our maps to that incredible something. They are invitations to look deeper, to question the fabric of reality itself, and to share the awe of that discovery with others. If this journey has reshaped your view of the cosmos, there are countless more mysteries waiting. Let us know which visualization reshaped your reality. And join us as we continue exploring the greatest stories the universe